Okay, welcome back. This is the part 4 of our lecture. In this part, we are going to discuss about empirical uh, cumulative distribution function. As I mentioned at the end of the last part, empirical cumulative distribution function is an estimate or estimator of the cumulative distribution function of a random variable. So to explain this, let us suppose that X is a random variable. It can be a discrete random variable or a continuous random variable with some unknown cumulative distribution function f of X or just f. Right here in this part, I am just using denoting it by f because we are talking only about one variable. There is no confusion of two variables. Right, so it's enough to use f in this case, capital F. Usually, in practical situations, this function is an unknown function. Right? We don't know the actual cumulative distribution function of a random variable. There's one way to estimate that, that is called the parametric approach, parametric method. There, we will have some data, and from those, we will, according to that data, we will assume some probability density function model for the probability density function like exponential, gamma, normal, uniform, that kind of thing with some unknown parameters. And then using the same data, we will estimate those parameters in the assumed model, and then we will consider that assumed model with those estimated parameters as the actual probability density function of X. And thereby we can get the cumulative distribution function F if we want. And then we can do the inferences using that estimated model. The second method is getting an estimate for the cumulative distribution function without assuming a particular model, like not assuming like x as a gamma or x as an exponential or x as a normal distribution and so on. So that is because there are situations where we don't have enough evidence or we don't have enough data to assume some model for the probability density function, and therefore we cannot use the parametric approach in that case. So in that kind of situations, we use a non-parametric method to estimate the unknown cumulative distribution function f. So this estimated cumulative distribution function using the data is called the empirical cumulative distribution function, ECDF. So to explain this, let us consider a random sample x1 up to xn from your distribution or the population. And suppose we have an observed set of values also, simple x1 up to simple xn. Right. So in this case, simple x1 up to simple xn can be considered as a realization of the random sample capital X1 up to capital Xn. Right. Now we will estimate the cumulative distribution function f using these data, observed data. So using the data, empirical cumulative distribution function is calculated as follows. Right. F hat x. F hat denotes the estimated f. Estimated cumulative distribution function is denoted by f hat. So f hat evaluated at some real number simple x is defined as the number of observations in our data set which are less than or equal to this number simple x divided by the total number of observations in the data set. So therefore, it is actually the sample proportion of observations in the data set which are less than or equal to this real number simple x, sample proportion. So this can be written in different ways. For example, if you denote the number of observations less than or equal to simple x by nx, then f hat x will be nx divided by n. That is one way to write down that, right? Uh, some books use this method to define f at x, that is 1 over n summation I from 1 to n I of xi less than or equal to x, where this I denote a certain function called the indicator function, which takes values 0 and 1 only, 0 or 1 only. I xi less than or equal to x will be 1. This whole thing will be equal to 1 if the observed value of xi is less than or equal to simple x. Otherwise, xi less than or equal to x, this whole thing will be 0, right? If the observed value of xi is greater than x, then this value will be 0, right? So when you are calculating this for each hi, for some i's you get 1, some i's you get 0, right? You get 1 whenever the corresponding observation is less than or equal to simple x. So therefore, when you add those values I from 1 to n, you get the number of ones. So that means the number of observations which are less than or equal to simple x. So that gives you nx. When you divide that by n like this, then you get again the sample proportion of observations which are less than or equal to simple x. Right. So that is the way to define it, right? Empirical cumulative distribution function, right? So now let us look at a situation to further understand what kind of shape this function will have, right? So suppose you have observed values x1 up to xn, x1 up to xn, and you have put them in the, suppose you have put them in the ascending order, and thereby you have found out the order statistics, the first order statistics, second order statistic, third order statistics, and so on. X first order statistic x within bracket 1 as a subscript is the smallest observation, the largest one, and in the middle there are other order statistics. So if you consider this in the definition, this x can be any real number. If you take this x to be any real number less than the first order statistic, at that point, f hat x will be equal to the number of observations less than or equal to that particular x divided by n. But in that case, the number of observations less than or equal to that particular x will be 0, because this x we are considering is less than the minimum observation in the data set. So therefore, f at x will be equal to 0 in that case, if the considered x is less than the first order statistic. If the considered x here is equal to the first order statistic, at that point, f at x will be equal to the number of observations less than or equal to the first order statistic divided by n. So number of observations less than or equal to the first order statistic will be equal to 1 divided by n. And then if you take x to be any number greater than or equal to the first order statistic, but less than the second order statistic, right? In that case, the number of observations less than or equal to x will still be 1. For example, if you are considering a continuous random variable, usually these x1 up to xn are going to be different values. Very rarely only the same number will occur twice, right? So therefore, in that case, still the number of observations less than or equal to x will be 1. So therefore, still the empirical cumulative distribution function will be 1 over n. If that x we consider here is equal to the second order statistic, At that point, the number of observations less than or equal to the second order statistic will be equal to 2. So therefore, this quantity will be 2 over n. Right? So like that, you can understand that the value of f at x is going to be the same in some parts of the function, and it's going to have some steps at each order statistic, right? At the first order statistic, it will jump from 0 to 1 over n. At the second order statistic, it will jump from 1 over n to 2 over n. Until that point, the f at x will be the same as 1 over n. Right. After the second order statistic, until just before the third order statistic, f at x will be equal to 2 over n. So at the third order statistic, it will take value 3 over n, like that. So therefore, you can understand that f at x is going to be a kind of a step function. Right. So therefore, if we plot these order statistics in the x-axis and the corresponding value of the f hat x on the y-axis, you get the graph of the empirical cumulative distribution function, right? So it will be a plot of I over n versus xi, where xi is the ith order statistic, right? So if we ignore any x value less than the first order statistic, then the function will, the graph will start at x1 value at that point. That means the first order statistic at that point, the value of the f at x will be 1 over n. And then until the second order statistic, it will have the same value. At the second order statistic, the function will jump to 2 over n, like that. So that is what the empirical cumulative distribution function should look like, a step function. So to further understand this, let us look at an example where we have a data set from the book, contains the times recorded by a computer server for 100 hits during a typical day. Right. So whenever a customer enters the website, then there will be a hit, and the website records that time. Right. So, for example, suppose the day starts at 12 o'clock in the night, and then we count the time from there. So 12 o'clock will be considered as 0 point, and then until the next day, time will be measured in hours. So the time can be anything between 0 and 24. We will have several uh, values where different customers have entered the website, right? So for the whole day, there may be more than 100 observations, a population of values. Here, we are given only 100 of those values. Therefore, we can consider it as a random sample of those X values coming from a certain population. So X is the time at which a randomly chosen website hit occurs during a given day, right? So then X can be between 0 and 24. Right? So I have 100 observations between 0 and 24. I want to now find out the order statistics. Therefore, I have to put the data in the ascending order first. So that thereby I can find out the X within bracket 1, that is the first order statistic, second order statistic, third order statistic, and so on. Because these times are continuous, usually they will be different values. Only very rarely there will be equal value. Most probably all of them are different values. So you will get the order statistic, and each order statistic you can find out the corresponding f hat x value, right? F hat x value will be I over n, corresponding to the first order statistic. F hat x value will be 1 over n, corresponding to the second order statistic. F at x will be 2 over n, and so on, right? So how do we get this? How do we draw this graph in R? So here, actually, the book gives you this function, it has given this as web hits, the function name. The function doesn't have any inputs here, but there it has some commands. So let's understand the commands given in the book. So first of all, it reads the data from this data set again given in the book. The data set is called comwebhits.dat. So it is a data set with the extension dat, not like txt or xl or svc or whatever. Therefore, usually it's better to use the function scan to read the data. So we read the data and put it into a vector called x using the function scan. So scan, this is the file name. Then all the numbers will be put into a column name x. And then what I want is to find out the order statistics. In order to find out the order statistic, what we have to do is we have to put the data in the ascending order. So there are two ways to get the data in the ascending order. One easy way is to use the function called sort. If you use the function sort, it will put the data in the ascending order, right? So let me show you that using an example. Suppose you have, so these are not those data, but some other data. I'm going to consider some data coming from a normal distribution, for example. Suppose you have 10 observations, right? So all these numbers are actually, I think, usually they will be different numbers, but let's see whether there's any number occurring more than once. Just to find out how many, the frequency of each observation, we can use the function table within bracket x. So you can see that actually the frequency of each number in this case is 1, right? So these all are different numbers. Now, in order to put the data in this data set, actually not this one. This one is actually already sorted, but in the x we don't have the sorted data. X can have any order, right? So you can see this is the second one. This is smaller than this one, so they are not in order. But if you want to sort them, you can use this function sort. So that will put the numbers from the smallest to the largest. That is one way to sort the data. But the book gives you another method. Actually, it uses another command by doing that. It uses this way, this method to get the sorted data. X within square bracket order x. So it uses some other function, x within square bracket order x. So there it is using some other function called order x. So let's look at what this order x means. Order x, first of all. So I have x there. So let's see order x. Order x gives you these numbers. There are 10 numbers. Order x gives you these numbers. So let me again put x also. Right. So x is this one, order x is this. So what does this 10 means? If you look at this data set, the smallest number is this number. That is the 10th number. So therefore, the order in this original data set of the smallest number is the 10th. That is the place of the observation, 10th. And in this data set, the second smallest value is this number. Second smallest number is this number. So that is in the second place. In this data set, if you consider them, the third smallest number is going to be this number here, 39.76. Third smallest number, that is at the 7th place. That is why we have 7 here. So you can see that order x gives you the place of the original data of the ordered data, right? That means place of the smallest value, place of the second smallest value, place of the third ordered value, and so on. So therefore, it is actually the place of the order statistics. That is why it's called the order x, place of the order statistic. Right. So the 10th observation is the first order statistic. Second observation is the second order statistic. 7th observation in the original data set is the third order statistic, and so on. So if I type now x within square bracket order x, what it gives you is x within bracket this sequence of this vector. So that will give you x 10th value, x 2nd value, x 7th value, x 8th value, x 5th value, and so on. By doing that, it will give me the sorted data set again, right? So because it gives me the minimum value, the first, and second minimum value, the second value, third minimum value, which is in the seventh place of the original data set, will be now coming to the third place, and so on. So x order x will give me the ordered data set in the ascending order. So the book here is using that method to sort the data. So it could have easily used the function sort x, but it's actually introducing another function in this way, right? So we have to put the data in the ascending order. So that will give you the order statistic. The first value, now it's again naming the ordered data set also by x. If you want, you could have named it by some other letter. For example, you could have said ordered X or whatever, but the book is using the same label because we are not going to use the original data set in that order again. So what we need is the ordered data set. Therefore, we are using the same name, right? So in this data set, then after putting them in the order, first number will be the first order statistic, second number will be the second order statistic, and so on. So the fx hat values at each of those x values will be 1 over n, 2 over n, 3 over n, 4 over n, and so on. So if we plot fx hat versus x values, so that will be given by plot x-axis variable first, and then y-axis variable is fx hat. Then we can get a graph, but you have to mention what the type you want. Usually in a scatter plot, you don't use any type, you just want the scatter. But sometimes you want to connect each point uh, consecutively by lines. In that case, we say type equal to within bracket L, type L. But here what we want is the step function, step function. So we can get the step function by using the type S. So that is another option in R. You can plot X versus some other Y and get the step function by giving the type S, right? And then in addition, it wants to put a label for the X lab, because otherwise it will put X here, the original value name we give. But what we want is we want to change the X label. So it wants to give, it has time of the website hit, and it wants to denote it by H instead of X here. So that's therefore it's giving everything that we want as the X label within quotes. And then it wants the Y lab to be labeled, Y axis to be labeled as ECDF. And in addition to that, actually it wants to, this is not necessary, but here it is explaining how to get some other text content. If you want, in the middle of the graph somewhere, you can use the function text. And then you have to specify where do you want it. So this is the middle point of that text. Right? You have to specify here x equal to 15 and y equal to 0.2 will be the middle point of this text here. So this is the text here. I want to, it wants to write down as number of hits during 24 hours equal, and then use n, where n is found by the computer inside the program here. N is the length of x. N is the length of x, right? So it will combine these two things and prepare one line. That line will say number of hits during 24 hours equal, and then whatever the n will be substituted here. So that will be one sentence. The middle, the position of that sentence, the middle point of that sentence will be x equal to 15 and y equal to 0.2. Right. So when we give these commands, and when we consider this as a one function, web hits. So if I say web hits with bracket without anything, it will give me the graph. So this is the graph that I get from that function. right? So you can see that y-axis is labeled as ECDF, x-axis is labeled as time of the website hit, comma, h. Here is the sentence that it wanted to write down at the 15 and 0.2 point. So that is actually the mid of this sentence, right? So number of hits during 24 hours equal is one part, and then it has inserted the number n here 100. So that is, you can use, you can prepare that kind of sentence by using the command paste. Paste whatever the text you want, and then whatever comma, whatever the numbers you want to put in, and so on. You can combine them by using the paste. So this is the cumulative distribution function estimated. That is the empirical cumulative distribution function for the number of hits, not the number of hits, sorry, the time of hits. X was the time of hits, right? So what can we see from this graph? At the beginning, the the ECDF was increasing very slowly, right? So that means at the beginning, that means in the night, because we consider uh, uh, 12 in the midnight as the time zero, right? So until 5 or 6, actually there was no any value. The smallest value was around 5 o'clock, right? After that, there were several hits, but the time number of hits were not that high, so it was flat this amount. But after that, as the time passes, numbers went up, and therefore the proportion of observations less than or equal to a given value is going up steadily. And then after that, again in the night, again after 20 or so, that means after 8 o'clock in the night, again rates are the proportion is becoming smaller and smaller. I mean, the rate of increase becoming smaller, but at the end, it's coming to 1, right? After that, it will be 1 like this. At the beginning, it will be 0 like this, right? 0 before 5 or something, and then after this value, it will be 1. So this is the empirical cumulative distribution function. This is used as a non-parametric estimate in this case. This is a particular situation obtained from a particular realization. So this is one estimate uh, of the actual cumulative distribution function of x. If you take another random sample from the same population, I suppose population was larger than 100. So if you take another random sample of 100 observations from the same population, the shape will be roughly the same, but not exactly there, but shape will be roughly the same, right? So therefore, that will be another possible estimate, right? So the estimator is the f hat x, that is the empirical cumulative distribution function. But from that, from different samples, there will be different estimates. All those estimates will be somewhat close to the actual cumulative distribution function, right? So that is where I will stop this session, and then after in the next session we will look at some mathematical or statistical properties of the empirical cumulative distribution function. Right. Here I have considered a data set coming from a continuous random variable. In the discrete case, if you are observing a discrete random variable, it is possible for you to have the same observation occurring more than once, right? Few observations will have frequency more than once, but still the same idea can be applied. Therefore, I'm not going to separately look at that, but I encourage you to consider an example with some discrete data. You can create your data. For example, you can generate some random numbers using a Poisson distribution. In that case, there will be some equal values with more than one frequency. And then using the same method, you can understand how the empirical cumulative distribution function will be plotted, right? In that case, you will see that, for example, if you have 1, 1, 1, 3 times, and suppose that is the smallest value. So at the first one, cumulative ECDF will be 1 over. At the second one, empirical cumulative distribution function will be 2 over n. And the third one, it will be equal to 3 over n. But when you're plotting it, you are plotting it against 1. So there will be, in therefore, first one value will be 1 over n, and then at the same point, it will go up to 2 over n. At the same point, it will go over to 3 over n. So therefore, at the end, you will be starting at 3 over n value when x is equal to 1, for example. So like that, I encourage you to look at that kind of situation as well. So that's where I'm going to stop this section, this part. In the next part, as I mentioned, we will look at some statistical properties of the empirical cumulative distribution function. Okay, welcome back to part 5 of this lecture. In this part, as I mentioned earlier, I'm going to look at some properties of the empirical cumulative distribution function. But before I talk about theory, I would like to show you some illustrations here about the idea, to explain the idea about the estimator and estimate, right? So as I mentioned, the empirical cumulative distribution function defined by the equation 1 here is actually the estimator, right? I have defined it like this. F at x is the number of observations less than or equal to x, but here I denote it by capital Nx. So here what I mean is before observing before really getting the data, we can define a random variable, the number of observations in my sample, which will be less than or equal to x. So that is a random variable. Before observing, it's just a random variable. It can take any value, in this case, between 0 and n. Right. So when you define in terms of that random variable, this f at x will be a random variable. So that is what we call the estimator. Right. So from one sample, when I observe this nx, I will have some number divided by the total number. Then I will get a number here that will be my estimate of the cumulative distribution function at value x. If I take another random sample, uh, from that random sample, my estimate will be different, because this nx in that case will be different. So at the same x value, f at x will be different. So that will be another estimate. So from sample to sample, f at x for a given x can be different. So each of those possible values, different values, can be considered as an estimate, but they are coming from the same estimator. In other words, they are coming from the same formula, something like that, right? So just to understand this further, let's look at this illustration here. I have changed the previous function given in the book slightly. I want to be able to draw the empirical cumulative distribution function when I give the data set. So I write it as a function of x, where x will be the data set. So first I will sort the data x. So I will use the same name after sorting also, because as I mentioned earlier in the previous, uh, okay, I think I didn't. Yeah. Yeah. As I mentioned, I am going to use the sorted data set rather than the original data set. Therefore, I will call it x again. So I'll find out the number of observation in my data set inside the function. So let's say n is the length of x. So f at x will be 1 over n divided by n, as in the same function in the previous session. So I want to plot x versus f at x, right? So x is now the sorted data. So therefore, they are the actually uh, order statistics. So I'm plotting f at x values, fx hat values versus the order statistics. I'm using the step function rather than the lines. Now I have changed my labels. X lab I'm going to use as X, and the Y lab I'm going to write down as F subscript X hat X, right? This is how you give that. I have explained this thing earlier also to you. Use the function expression. Expression. Actually, hat has not come here correctly. I think probably I have made that wrongly. I will correct it later if possible. Uh, so this is supposed to be actually F hat X. Right. So what I'm going to do is now I'm going to show, consider two expressions, two cases where I will have my data, original data from a normal distribution first. I will have my sample size to be 25, n is equal to 25. So in this case, I'm considering a continuous random variable x. So let me take some random numbers from a normal distribution with mean 50 and standard deviation 10. I will round them. Uh, and still, all the numbers most probably will be different numbers. There will be, yeah, almost all the numbers will be. To check it, I will use table X. Yeah, you can see that all the observations, 25 observations has frequency 1. So that means all the observations are different. So that is the general situation whenever you are dealing with continuous data. Continuous data. So using this function that I have uh, changed here, I will now draw the empirical cumulative distribution function. So I get this. This is my empirical cumulative distribution function for the 25 observations. So you can see that it is a step function, right? So this axis, there is a step always at a order statistic. Now, actually, I'm going to draw the theoretical cumulative distribution function at the same x values uh, on top of this thing to see how different the estimated empirical cumulative distribution function, the estimated CDF, that is the empirical cumulative distribution function, and the theoretical cumulative distribution function. Because in this case, I know that X has a normal distribution with mean 50 and standard deviation. Cumulative distribution function at these X values can be obtained by using the P norm function. So I say CDF is equal to P norm, but I have to calculate them at the ordered X values. So I have sorted the X values and put them into Y first. Right. So Y contains the sorted X values, that is, those are the order statistics. So I'm going to calculate the CDF at those Y values from the normal distribution with mean 50 and standard deviation 10. So P norm function will give me the cumulative distribution function. Then I'm going to draw the cumulative distribution function versus those Y values. But you know, when the random variable is continuous, the theoretical CDF is a continuous function rather than a step function, right? Theoretical CDF is a continuous function. Therefore, I'm not going to use a step function here. I'm going to use the lines here, right? So what I'm going to do is I'm going to draw CDF versus Y and use the command lines. Lines is used to draw lines on top of a previously drawn graph. So I already have this graph. So I want to draw the CDF curve on top of this thing. I can use this command here, and I am going to use the color red for that. So this is the picture that I get. So the step function is the empirical cumulative distribution function. This is the actual theoretical CDF in red color. So you can see that empirical cumulative distribution function is somewhat above or below at each x value, and in different x values. At some points it's above, ECDF is above the actual value, and some points is below the actual CDF value, but you can see that it's around the actual CDF function. So therefore, this black step function can be considered as one possible estimate of this red curve. One possible estimate of this red curve. So this is coming from the particular data set I have obtained from this normal distribution. Now let me do the same thing using another data set, but from the same normal distribution. So I will again generate some random numbers from the same normal distribution, and based on that sample also I will draw the empirical cumulative distribution function. So I will again generate some other random numbers. So these numbers are also quite different from each other. Frequency will be one. Each number is different. You can see that. So from that, those data, I will get my empirical cumulative distribution function. So now from this data set, my empirical cumulative distribution function is this step function. Earlier, it was this. So to compare with the theoretical one, again, I will get the same theoretical CDF again and draw it on top of this. So these two these two red curves are the same actually in both graphs, but the step functions are different. Here, this is the empirical cumulative distribution function obtained from the first data set. This is the empirical cumulative distribution function obtained from the second data set. So you can see that they are not the same, they are different. But there's one common property that the step function, empirical cumulative distribution function, is going to be around the red curve, right? At some points, the empirical cumulative distribution function is above, little above the red curve. At some points, is below the curve, right? So if I do this again and again and again several times, you will see different ECDFs, but all of them will be roughly around the curve. So each of them separately can be considered as an estimate, right? If one person get the first data set, his estimate will be given by this step function. If the second person gets the second data set, his estimate will be this. So the first person will say, okay, my estimate is this step function. The other person will say, my estimate is this one. So estimates are different, but you are using the same estimator in this case. Same estimator, because number of observations is the same. The formula that we are using is the same, method is the same. So that is the estimator. But from sample to sample, estimates will be different, right? So that's the situation that you will see when the data are coming from a continuous distribution. Let's now consider the situation when the data are coming from a discrete distribution, like a Poisson distribution. So I'm going to consider the Poisson 5 distribution, Poisson distribution with rate parameter 5. Again, I'm going to consider only 25 observations. Otherwise, the step function will not be very clear. Steps will not be visible, right? Like in the previous graph, when n was 100, steps were not that visible. It was almost like a continuous curve, right? But when you have small number of observations, you can see that clearly the empirical cumulative distribution function is actually a step function. So let me generate some 25 random numbers from a Poisson 5 distribution. In this case, it is possible for some observations to be having more than one frequency, will be more than one, right? For example, let's look at the data itself. X. So you can see that there are several fives, several ones, several fours, and so on. So just to see the frequency table, table X, it shows that there are 3 ones in the data set, the 3 twos, 4 threes, 2 fours, and so on. So when we are calculating the empirical cumulative distribution function for this thing, how do we do it? Well, so the ordered data set will have 1, 1, 1, 2, 2, 2, 3, 3, 3, 3, 4, 4, 5, 5, 5, 5, 5, 5, because there are 6 fives and so on. So that will be our ordered data set. So at the first one here, empirical cumulative distribution function value at when x equal to 1 will be 1 over 25. At the second one, so still x is equal to 1, the cumulative distribution function, empirical cumulative distribution function value will be 2 over 25. At the third one, the value of the empirical cumulative distribution function will be 3 over 25. So when you draw the curve, first at 1, we will have the value 1 over 25. And then again, it will draw, in that case, there will be no going along the horizontal line. Vertically, At the same x equal to 1 value, it will jump to 2 over 25 value. And at the third one, again, it's not going horizontally, still at the same x value, x equal to 1. Now the empirical cumulative distribution function value will be 3 over 25. So when you look at the graph, it will see that the first point, you will have a vertical line, right? And then the last point is 1, x-axis is 1, y-axis is 3 over 25. And then it will go alone until the next value is 2. So there are three values of 2. So again, empirical cumulative distribution function will again go vertically and then come horizontally. So let's draw that. Empirical cumulative distribution function. So these are the x values, the table. I will draw the empirical cumulative distribution function. In that case, you can see that at 1, it was going up first. So at the first value, it was for the first one value of empirical cumulative distribution function is 1 over 25. At the same point, the second value will be 2 over 25. At the same point, again, the third value will be 3 over 25. Now it goes to the fourth value, that is x equal to 3. So again, there are two values. So therefore, the first value here will be 4 over 25 and then 5 over 25 and like that. So this is the empirical cumulative distribution function coming from that. So to compare it with the theoretical cumulative distribution function, I will get the theoretical cumulative distribution function at these y values, right? I am going to calculate the empirical cumulative distribution function at those values when the data are coming from Poisson phi distribution, right? So I will calculate the CDF by using p poise at these sorted x values, that's I call y, and then the lambda value is lambda. So CDF, right? And then in this case, we are dealing with a discrete data set. So, like in the previous situation, it is not suitable to draw the theoretical CDF by connecting the points using lines, right? It's not going to give you, it's not suitable to draw a continuous CDF because we know for a discrete random variable, CDF is also a step function. We have discussed this thing sometime earlier in our course. I have explained that, right? For a discrete random variable, the theoretical CDF is also a step function. So in order to get that theoretical CDF, I will use lines y, that is the set of x values, sorted x values, and the CDF value. Type will be S now because I want the step function, right? Okay, what happened? It didn't run. Okay, I didn't calculate CDF, right? Okay. Oh, something is wrong. Why is that? So let me go through it again. Okay. Yeah, in that case, I code. So let me do it again to get it with the curve, the graph in the first. So, right. So this is the empirical cumulative distribution function for that particular data set that I generated now. And then this is the theoretical CDF for the Poisson phi distribution evaluated at those observed values, right? So you can see that there is some differences, but still, right? In this case, most of the empirical cumulative, almost actually everything, all the empirical cumulative distribution functions is above the theoretical value. Right. So let's look at so that is, but anyway, that in that case we can consider this black step function as an estimate for the red step function. You can see that there is no much difference the maximum difference is somewhere here. Other differences are smaller than that. So let me draw the empirical cumulative distribution function again using a different sample. So let me take a different set of x values. So these are my x values now. Again, you can see there are some observations repeating, right? For example, uh, there are 4 3s and 2 4s and so on. So let me draw the empirical cumulative distribution function, right? So that is the empirical cumulative distribution function. So let me now draw again at those points the theoretical CDF. So you can see that in that case, theoretical distribution is above this one. So you can see that from sample to sample, empirical cumulative distribution function can be different. But I think it's better to draw the empirical cumulative distribution function not only at these observed values, because theoretical CDF can be calculated at any uh, x value. So therefore, I will now further draw the CDF at all possible x values between the minimum and the maximum of this sample. So let me take the minimum of x to be min x, for example, min dot x, and the maximum of x to be max dot x. Right. So now I will take my y to be all the rounded values, because I want the integer values, rounded values between min x and max x. Right. So that will be giving me all the possible integers, not only the values observed in my data set. I will consider all the possible values between the minimum and the maximum of the data set, and I will round them uh, because I want to get the uh, full numbers, because these are integers. But there is something wrong. What is the error here? No, error has disappeared, right? So why? I will calculate now theoretical CDF, and then I will repeat this step. Right. So now, for example, I have y values, right, at these points, and then I will calculate the CDF at those points, and then draw the lines. That happened. Okay, let me go through this again just to see. Right, x, x, x. So I have a data set. Y is the sorted data set. So I'll skip this one. I'll come to this one, min x, max x. Y is the rounded values from min x to max x. So CDF is going to be the cumulative probabilities theoretical values. So if I draw lines now, Y CDF type S, what do I get? Yeah. So this is the theoretical function, theoretical CDF evaluated at each possible value between 2 and 9, because my data set min x is equal to what? Let's see, min x and max x. So in this particular data set, min x is 1, max x is equal to 9. So what I have drawn in red here is the uh, theoretical cumulative distribution function of a Poisson 5 distribution when x is between 1 and 5. So now you can see that actually the observed empirical cumulative distribution function can be above or below the actual theoretical CDF. So let me do it again for a different data set and see how the estimated CDF, that is the empirical cumulative distribution function, changes. So I have got a different data set now. These are my data. This is the table again. So there are some frequencies more than one. That's okay. So I'll draw the empirical cumulative distribution function of that data set. I will just delete these three lines here because I'm not going to look at. So now I will find out the minimum of observation in my data set and the maximum observation in my data set, and I will get the y values to be all the integer values between minimum and maximum, and then I will calculate the theoretical CDF at those values of a Poisson 5 distribution. So I will now add the theoretical CDF. So you can see that again, theoretical CDF here and here are the same actually, because I have calculated the theoretical distribution between in some two values. Using the Poisson 5 distribution, using the same distribution, therefore theoretical CDF is the same. You can see again the black step function, which is the empirical cumulative distribution function, is above the red step function at some points and below that some points. So you can see again the empirical cumulative distribution function is around the theoretical cumulative distribution function. So here this is black one is the estimate of this red curve. In the second graph, the black one is the estimate of the red graph. So you have two different estimates coming from the same estimator. Right. So I wanted to explain that idea. I think now it's clear to you. So now, do I have time? No, I think I have run out of almost all the time. So therefore, I will explain these theoretical properties of the empirical cumulative distribution function in the last part of this section of this lecture, right? Okay, let us again start the last part of the lecture. This is part 6. Let us now look at the theoretical properties of the empirical cumulative distribution function. Let us now consider a fixed value of simple x. And let us consider f hat evaluated at that x. That is the empirical cumulative distribution function evaluated at that x. Right? So as we have already mentioned, f hat x can be considered as an estimator for fx. Right? Fx is the theoretical unknown cumulative distribution function evaluated at x. That is the unknown value. F hat x is the estimator of that value, unknown value. So f hat x, when considered as the estimator, it is a random variable. So it has some probability distribution. Any random variable has a probability distribution. So it is meaningful to talk about the expected value of that random variable, variance of that random variable, and other moments of that random variable, distribution of that random variable, and so on. So now let us look at the expected value of f hat x. Remember, f hat x is equal to nx divided by n, right? We defined f hat x to be nx divided by n, where nx is the number of observations in our random sample which are less than or equal to simple x. Now, suppose we have a random sample from some distribution. We don't know the distribution, therefore we don't know the density function, or we don't know the cumulative distribution function, but some fx has some distribution. We are observing taking n observations of x. Suppose you have n observations, right? So then we want to look at in this particular sample, the number of observations less than or equal to the given value simple x, right? So this is, we are interested in this random variable, right? Expected value of, but we are really interested in the expected value of f hat x. That is equal to expected value of nx over n, right? But here n is a fixed number, therefore this is equal to expected value of nx divided by n, right? So what is the expected value of nx? Nx is a random variable. Nx is the number of observations less than, in our particular sample, which are less than or equal to the value simple x. Now, we have these observations, n observations taken from the same distribution. Therefore, each observation, there is a probability that each observation is less than simple x. The probability that x1 is less than simple x is some value. We don't know that value. There is some value. Let's call that theta, because we don't know the value. We unknown constant. And there is a probability that x2, the second observation, is less than x. And that will also be theta, because x1 and x2 are coming from the same distribution. They have the same distribution. And similarly, there is a probability that x3 less than or equal to simple x. That probability will also be theta. So therefore, uh, nx, the number of observations less than or equal to x, will have some distribution with probability theta. What is that distribution? We are looking at n observations. Out of that, some number of observations will be less than or equal to x. The other ones are greater than x. Right? So if you consider each observation is either less than or equal to simple x or greater than simple x. Right? So this is like a success or failure. We are looking at n observations. Each observation can be considered as a success or failure. Probability of a success is equal to theta. The probability that any observation is less than simple x is theta. We don't know the value theta, but let's consider it theta. Right? But in this case, what is theta? Theta is the probability that any xi is less than or equal to simple x. Right? So even though we don't know theta, we know that it is equal to fx. That is the cumulative distribution function evaluated at simple x. Right? Because we know that the probability, right? So the probability that, let me try to write down it here. So probability that x1 less than or equal to simple x is the same as probability x2 less than or equal to simple x, and all these are equal up to probability xn less than or equal to simple x. These all are the same as fxx, the cumulative distribution function, which is of course unknown, right? So therefore, we can say this nx has a binomial distribution with number of trials equal to n, and the probability of a success theta is equal to fxx. This nx has a binomial distribution. Nx is a random variable. So therefore, we know that expected value of nx is equal to n times theta. N times theta. So that is equal to n times fxx. Variance of nx in that case is equal to n times theta times 1 minus theta. So that is equal to n times fxx times 1 minus fxx. Right? So this is our theta here. Theta is the probability of a success. In this case, success being the observation less than or equal to simple x. So therefore, expected value of nx is equal to n times fx. Right? Therefore, expected value of f hat x is equal to expected value of nx over n. that is equal to n times fx over n, which is equal to fx. Right. So notice here, this is a very interesting result. The expected value of the empirical cumulative distribution function evaluated at x is equal to the theoretical CDF evaluated at x. Let me delete these things first. So what does it tell you? Expected value of the cumulative empirical distribution function of f empirical distribution function f hat x is equal to fx. So this is something that we want to estimate some unknown quantity. This is the estimator of that quantity, right? So this is like a parameter, unknown constant. So this is the estimator of that thing. And we have shown that the expected value of the estimator equal to what we want to estimate, parameter, right? So therefore, usually for any random variable, we know the possible values of that random variable are around its expected value, right? For example, in general, if you consider a random variable x, suppose its mean is mu, then the possible values of x are going to be around. Some values are going to be less than mu, some values are going to be more than mu. That's what I mean by around. It's not saying that it's exactly in the middle or something. It's around. Some values are less than that value, some of them greater than that value. So this is an important result. Expected value of the estimator is equal to the parameter. So that practically implies to us when you look at all possible values of f at x coming from different samples, if you consider different samples, some of them will be above fx, some of them will be below fx for this particular x, right? And the mean of all those possible values is actually equal to the quantity that you want to actually estimate. So this is a very important property of an estimate, right? Estimator, right? Estimator is a fixed method or formula. We can get different estimates from that estimator. So this means on average, the set of all possible values of that estimator is equal to what we want to estimate. This is considered as a very desirable property of any estimator. That property is called the unbiasedness. So here, f hat x, which is the empirical cumulative distribution function, is an unbiased estimator of fx. This is true for any x. Here we have taken a fixed x. If you consider any other fixed x, at that x also, this is true for that x. So therefore, in general, this whole function can be considered as an unbiased estimator for this whole function, right? Here we have proved that for a fixed x, expected value of this quantity is equal to this quantity. But you can consider another fixed x. For that x also, this will be true. Another fixed x, for that x also, this is true. So in general, for any x, this is going to be true. Therefore, we can say that the empirical cumulative distribution function is an unbiased estimator of the theoretical CDF, cumulative distribution function. That is one important result. Now let us look at the variance of this f at x. Variance. So going down. Okay. Now, what is the variance of a binomial random variable? As I mentioned, it's going to be n times theta times 1 minus theta. So here, variance of f hat x is equal to, okay, let me try to write down here. How do I write? So this will be equal to variance of nx divided by n, which will be equal to 1 over n square times variance of nx. Right? So this is equal to 1 over n square Okay, where is this? So this is equal to 1 over n square. Variance of nx is equal to n times fxx times 1 minus fxx. Right. So this is like n times theta times 1 minus theta, but this cancels out. So therefore, variance of f at x is equal to fx times 1 minus fx divided by n. What does it tell you? It tells you that it's also a very important result. You can see that what happens to the variance of f at x as n goes to infinity, or when n increases, what happens to the variance. So you can see that when n increases, right, if you consider a larger sample, then the variance of f at x will be smaller, right? So if you increase n to infinity, this thing will be 0, right? So expected value of fx hat is equal to fx. Variance of fx is in general a function of n, but this variance will reduce when n is increased. So this property, that the variance, so for an unbiased estimator in this case, there's a very important result. When the variance is decreasing, that means when the variance of some estimator goes to 0 as n goes to infinity, this is another desirable property of any estimator, or not only for this particular estimator f hat x, for any other parameter. If you consider some estimator, if that estimator has this property that the variance of the estimator goes to 0 as n goes to infinity, that is considered as a desirable property. Why? Because variance gives you the idea about how far away your estimate can be from the actual parameter that you want to estimate, right? It gives you a measure of the error of your estimate. If the variance decreases as n increases, that means your estimate is going to have a small error with a high probability, right? So that is a good thing, right? If the estimate, your estimate is going to have a small error with a high probability, right? Error will be small with a high probability is a good property. So that property is called consistency. Consistency. So in this case, we say f hat x is a consistent estimator for fx. So we have shown that f hat x, which is the empirical cumulative distribution function, is an unbiased estimator for fx, and also it is a consistent estimator for fx. So those two are very good properties. People consider those are desirable properties of any estimator. Now, let me show you this thing using an illustration graphically, using some simulations. Right. So let's look at some estimator, that means empirical cumulative distribution function of some known CDF, because I am going to assume that some random variable has a known distribution, because in order to see this thing, demonstrate, in practically we don't know the actual theoretical distributions, but here let us assume that we know that distribution, and therefore we can look at the actual CDF and the different estimates of CDF. When n is increased, what happens to it? So that's what I'm going to look at. So let me first look at situation where the data are coming from a normal distribution with some normal distribution with a given mu, non-mu and non-sigma. In practical, you usually don't know the mu and sigma, but here I'm going to assume that the data are coming from a normal distribution with mean 50 and standard deviation 10. So I'm going to now draw some using some function here that I have. I have written a function to draw the empirical cumulative distribution function when you have n observations, and also on top of that the theoretical CDF. So let's consider a situation where your sample size is 10, data are coming from a normal distribution with mean 50 and standard deviation 10. I'm going to look at the empirical cumulative distribution function and the theoretical CDF in that situation, and then I'm going to increase my sample size to 20. I'm going to do the same thing with sample size 40, and I'm going to do the same thing with sample size 100. So the first one, this is when n is equal to 10. You can see this is the step function, that is the estimate. This is the theoretical one. So you can see that there is a somewhat bigger errors at different x's. So for example, in this x, the error is small for this particular case, but for this x, error is large. So let's look at now what will happen if you increase n to 20. So in this case, you can see that the vertical error has now become little less, still not that small, but less. If you increase sample size 40, now you can see empirical cumulative distribution function is very close to the theoretical CDF. If you even increased n equal to 100, now even close, right? So you can see that the variability is decreasing, and the expected value is going to be equal to the theoretical one. That means some of the values are above, some of the values are below, and therefore expected value will be equal to the theoretical value. So that is a situation where the data are coming from a normal distribution, continuous case. Okay, so now let us look at a discrete case. I am going to assume that the data are coming from a Poisson distribution with rate equal to 5. So I will do the same thing. Now only difference here is the theoretical CDF also will be a step function, right? Because this is a Poisson, that is a discrete random variable. So I'm considering n equal to 10 situation. So the the red one is the theoretical CDF, black one is the empirical CDF. Here, what happens when n is equal to 20? This is when n is equal to 40. This is when n is equal to 100. So you can see that they are becoming more and more close to the theoretical one. Empirical CDF is becoming more and more close to the theoretical one. So that's what I mean by consistency. When n is increased, the variability around the theoretical CDF is going to be smaller and smaller, right? So that is a very important theoretical result telling us that empirical CDF is a very good method or very good estimator as an approximate function for the actual CDF, right? So this is here. When we calculate empirical cumulative distribution function, we don't assume any theoretical distribution generally, even though in these simulations I have to assume, because otherwise I cannot generate the data. But in general formulation of the empirical cumulative distribution function, we don't consider any distribution. We just take the number of observations less than or equal to x divided by n, right? Whatever the distribution doesn't matter, right? So that's why we call it a non-parametric estimate. We are not assuming any parametric distribution, right? So that's the theoretical property, right? So now quickly let me go through some applications of this empirical cumulative distribution function. There are in several areas, empirical cumulative distribution function is used for various purposes. For example, when you have a data set, you can use empirical cumulative distribution function to calculate some probabilities and also to calculate some quantiles, right? So that is the most preliminary application. But empirical cumulative distribution function can also be used to compare the actual distributions of two random variables. Suppose you have x and you have some data set. You don't know what the actual distribution of x is. You have another random variable y. For example, suppose you are considering the heights of people in Sri Lanka and some other country. You want to look at whether the distributions of heights, for example, males of males are the same, right? So you want to compare the actual distributions of two random variables. You have some data from both countries, but you don't know the actual distribution. So you can use the empirical. You can compare the empirical cumulative distribution functions, right? So for example, suppose you have empirical cumulative distribution function of one data set is like this. Empirical cumulative distribution function for the other data set is like this. So you can see that there is a quite large difference between the two cumulative distribution functions. But in some places the difference is small, some places the difference is large. So usually in this case we look at the largest vertical distance. If the largest vertical distance between these two is larger than some pre-specified values, we will decide that the actual distributions of these two random variables are quite different. If the largest vertical distance is smaller than some pre-specified value, we will decide that, of course, always there will be some differences, even though exactly if you have two random samples from the exactly the same distribution, still there will be some differences in the empirical cumulative distribution functions. That is natural, right? So, but what we look at is whether there is a very large, significantly large difference between those two. That's why we are looking at the maximum. If the maximum vertical distance is larger than some pre-specified value, we decide, okay, this is a significant, statistically significant difference, and therefore, in the populations, the distributions must be different. Right, so we will talk about this kind of statistical tests in more detail in the next part of this course, that is going to be the statistical inference. But here I'm giving you the rough idea application. So you can use the empirical cumulative distribution function to compare the actual distributions of two random variables. That is one application. Another one is sometimes we are assuming some distribution for the data. For example, we are going to assume that our observations have an exponential distribution, right, with some given parameter, right? So in that case, what we can do is we can draw the actual cumulative distribution function of that assumed distribution, and also we can draw the empirical cumulative distribution function from using our data, and then again we can look at the vertical distance between the actual cumulative distribution function that is related to our assumed distribution, and also the empirical cumulative distribution function coming from the data. And if the maximum vertical distance is again greater than some pre-specified value, we decide that our assumption regarding the distribution of our data is not reasonable, not good. But if the vertical distance, maximum vertical distance between these two is somewhat small, then it may be reasonable to assume that actually our data, it's reasonable to assume the assumed model is a good model, right? So like that, we use the idea behind these differences between the two empirical cumulative distribution functions, or this vertical distance between a theoretical and a empirical distribution function, to test whether a given assumption is reasonable or whether two distributions are the same, right? So we will talk about this test based on this vertical distance in empirical cumulative distribution function is called the Kolmogorov-Smirnov test. So we will talk about that test a little later in the statistical inference part. Right. So in addition to that, empirical cumulative distribution function is also used in relative reliability and survival analysis, statistical process control, and so on. In all those cases, usually to test the assumptions regarding the distributions and so on. Right. In addition to that, the empirical cumulative distribution function is used to detect outliers, and in some other non-parametric test of analysis. And therefore, this empirical cumulative distribution function can be considered as a very useful distribution-free estimator. That is a non-parametric estimator. Distribution-free means we are not assuming, we don't have to assume a particular distribution for the data to calculate the empirical cumulative distribution function. So that is a very big advantage, right? So that's a major advantage of the empirical cumulative distribution function. It's a very simple thing to calculate. It's a non-parametric estimate of the theoretical CDF. So that's where I'm going to stop this part of this lecture, and that ends the whole lecture six parts of this lecture, right? Each part was around 30 minutes. So altogether 3 hours. So that's the end of this last part, section 6.